Hi there, welcome back to this channel. In this video, we are going to be talking about differentiation or differential calculus. Now, a brief history about calculus. The concept of calculus was developed independently by two scientists in the 16th century, and they were Isaac Newton, Sir Isaac Newton, and Gottfried Leibniz. Sir Isaac Newton claimed to discover his in 1666 when he introduced his idea on the study of fluxions, when he was studying fluxions, but he didn't publish his paper until 1693, while this guy, Gottfried Leibniz, was forced to publish his paper in 1684. And of course, there was an argument about who discovered the concept, because, you know, this guy claims to discover it first. But the idea now is that the notations we use for calculus were the ones invented by Gottfried Leibniz, because his own concept was a simplified, a simpler concept, of a simpler approach rather to the concept. Is that okay? Now, that's basically it about the history. So now, why do we take differentiation, or what is differentiation about? Now, differentiation, or basically generally calculus, is the mathematics of change. So we'll call it the mathematics of change, because primarily what it measures is how quantities change, or how the change in one quantity affects the change in another quantity. You already know that in the study of lines, the Cartesian geometry, or where we did coordinate geometries, we talked about the fact that when we want to study the rate of change of two quantities, especially one that is related linearly, we simply use the gradient or rate of change or the slope. Those are the possible names you might find for this same guy. Gradient, the slope, or the rate of change is equal to the rise over run for any graph that is linear. Does that make sense? So we're going to have the rise over run. And what that means is that the rise is going to be the change in y-axis over the change in x-axis. Okay? Now, if this is the case, what is the change in y? How do you measure the change in y? The change in y is going to basically be y2 minus y1 over x2 minus x1. So that is going to be our formula for calculating the rate of change. That is for a linear function. Now, how did the concept of differentiation now come about? It came about when scientists tried to calculate the rate of change of a curve, and it became impossible. So now, at that time, it had been easy. They had found it easy to calculate the rate of change of a straight line. But how about a curve? Okay? So consider this graph, for example. Consider this graph. If I have a graph like this, for example, and I said you should calculate, and I have a curve like this, and I said you should calculate the rate of change of this curve. Now, what was discovered was that the rate of change of this curve was different at every point, simply because it's a curve. The rate of change of this curve is different at every point. So the idea they applied was that, now, we draw a chord here, a chord. So the idea is that the gradient of this chord can tell us what the gradient of this curve will be at a particular point. So notice, we cannot take one gradient does not work for the entire curve simply because the gradient changes as the point changes. Does that make sense? Okay, so let's call this point P, for example, and let's call this point Q. If we wanted to take the rate of change at point P, now here's what we'll do. Now, there is a line that touches point P only once, and that is the line that is going to have an equal slope with point P. Is that okay? Now, if we draw this chord here, this line here, this line is going to be called a secant. Does that make sense? It's going to be called a secant. So if I wanted to take the slope of the secant, so the slope m of secant now, my secant, that is this line, is going to be the rate of change of my secant line in y-axis, the y-axis of my secant line, to the rate of change in the x-axis. So the first thing to do is to define this line, this our secant. So this point here, let's say it corresponds to a particular value x. And when you plug in x value into a particular function, you are going to get a y value. So let's call the y value our f of x. Now, what we want to do is, we want to take another point on that curve that is very close to P, but I'm expanding it here. Is that okay? Now, that is very close to P, but we said it's very close to P. Now, that point is going to be a little change that will be added to the x. Is that okay? We're going to add a little more value to that x value, and it's going to give us a new y value. Okay, so this point, let this point be x plus a little change in x. Does that make sense? X plus a little change in x. So it means that from here to this place is our little change in x. Does that make sense? So it therefore means that this portion, this point here, will correspond to f plus x plus a little change in x. Does this make sense? Now, if this be the case, then we know that the slope of our secant, m secant, I shorten to sec, is going to be the rate of change of y-axis, which is f of x plus dx minus f of x all over x, that is change in this guy. Now the change in this guy is going to be x plus dx minus x. I mean, by the time we take care of this, then m sub secant is going to be f of x plus dx minus f of x all over dx. Now, this is the slope of the secant line. This is the slope of the secant line. So how do we get the slope of this curve at point P? Since we already know that the slope will change at every point. If we wanted to get the slope at point P, how do we do that? Now, this is what you do. This is what scientists did. Now, let's take this point Q. Let's bring it closer and closer to P as much as possible. Let's say, for example, if we bring it to a point here that we call Q1, and we bring it close again to a point here, Q2, and bring it to a point here, Q3. Which point there is going to be the closest to point P? It's going to be obviously what? Point Q, isn't it? And what that means is that the slope at point Q3 rather, is going to be close as much as possible to the slope at point P. Okay, so it therefore means that we are bringing this line to a point where it becomes the tangent at point P. So it becomes the tangent at point P, then we now have that the slope of the tangent, which will be the slope at point P, will be equal to, you know that if we bring this point Q closer and closer to Q P as much as possible, there's going to be a time where the difference between point P and point Q that we are moving close to it is going to be infinitesimally small. By the way, that's the meaning of calculus. We call it infinitesimal calculus. It studies different minute changes. Okay, so it's going to come to a point where it is very, very close, and the closeness and the difference between them will be insignificant, or we say it's infinitesimally small. So by the time it gets to that point, we will say that we have gotten what? The slope of the tangent. Or we say that it is that point where dx is closer to 0. Why? Because as we are bringing Q close to P, our dx value is reducing. Does that make sense? Our dx value keeps reducing. So therefore, our m tangent is going to be the limit that our function, this function, approaches, the limit that our m second approaches as dx approaches 0. Does that make sense to you? Our m tangent, the slope of the tangent at P, is going to be the slope, is going to be the limit of the slope of the secant as dx tends towards 0. Okay, so our m tangent therefore becomes m sub tan is going to be the limit of f of x plus dx minus f of x all over dx as dx approaches 0. Now note, dx never really becomes 0. It only gets closer and closer to 0. Okay, now let's now talk about how we use differentiation, how we solve questions using differentiation. So for example, we call this the first principle of differentiation, and that's what we're going to be using to evaluate some functions now. Okay, so for example, if a question says you should find the slope of the tangent to the curve y equal to x squared, f of x equal to x squared. The first thing you should note is this: there are many notations for dy dx. The first notation for differentiation, rather, the first notation is the f prime of x. So that equation that I wrote down there is the equation of f prime of x, or dy dx, or y prime, or dy dx, something like this. Is that okay? So these are the possible notations you might see. They are basically referring to the same thing. All right. So in this case, our slope of our f inverse of x, of course, is going to be, first, let's evaluate some things. If x was x, a little change in x, which will be x plus the little change in x, is going to be the square of this guy. Does that make sense? The square of a little change in x, which will still be it will still be close to x squared. Does that make sense? This change is a very insignificant change, as small as 0.00000000001. So something as small as that is more like it's still 0, isn't it? It doesn't really affect x that much. Is that okay? So, but we want to account for it. That's why we're including it. We want to account for it. So in that case, we're going to square this. And by the time we square this, we're going to have that we're going to square this. X squared becomes x squared plus we multiply this guy by this guy by this guy. X times dx, x dx times 2, 2x dx plus dx squared, dx squared. Okay. All right. So if my f of x is this, my f prime of x, f prime, my f of x is this, that's what I'm saying. Then f of x plus dx will now be this. Does that make sense? Let's now revise our equation. F prime of x will now become what? The limit as x as dx tends towards 0 of our function f of x plus dx minus f of x all over dx. If this is the case, then f prime of x is going to be the limit as dx approaches 0 of, now what is our f plus x plus dx? If our f of x is x squared, our f of x plus dx will be what? X squared plus 2x dx plus dx squared. So that will be x squared plus 2x dx plus dx squared. Okay, all of, okay, that is our f of x. Then minus f of x. What is f of x? F of x is x squared. Okay, so f of x is x squared. Then we have minus x squared. Okay, now all divided by dx. Okay, now if that's the case, then we have that f prime of x will be equal to the limit as dx tends to 0 of, by the time you open up this bracket, this guy is going to take care of this guy. Then you'll be left with 2x dx plus dx squared over dx. By the time you simplify this fraction, this guy, so that each guy will be a fraction on its own. What we have is basically we are distributing the denominator. That's what I mean. So f prime of x will be equal to the limit as dx tends towards 0 of 2x dx over dx plus dx squared over dx. Dx takes care of dx, and of course dx takes care of one dx from here. There are two dx's here. So what will that become? This will be f prime of x will be equal to the limit as dx tends to 0, as dx becomes 0, of 2x plus dx squared. So if dx is tending towards 0, is approaching 0, it means that dx, okay, sorry, square has gone. It means that dx does not have any significant change that it will bring to 2x. So therefore, we can say dx will become 0. Will become so insignificant that it will be equal to what? To 0. If that be the case, then the limit as dx tends to 0 of 2x. So when dx tends to 0, then our f of x, f prime of x, will be equal to 2x. And so that is the answer for f of x is equal to x squared. Okay? Now, let's try one more function. So, let's say we are given y or f of x to be equal to x cubed plus 3 or plus 4, for example. Anything, you know. Okay, let's say we are given something like this. So if this is f of x, what will f of x plus dx become? F of x plus dx will be equal to x plus dx cubed x plus dx cubed. Okay? Let's say there was one x here too, so that you will know that it is the same. Let's say there was x here too. It will become x plus dx rather, then plus 4x dx. Alright, this just to make you know that when there's a, if this was not a constant, if it's actually an expression that carries x, then it will still affect it. Is that okay? F of x plus dx will affect even this guy, not just this guy. Is that okay? So our first the first work to do is let's express this guy in full. This becomes x plus dx into bracket x plus dx squared all squared plus 4x plus 4 dx. Okay? If this is the case, then f of x plus dx will be equal to x plus dx into bracket x squared plus 2x dx plus dx squared plus 4x plus 4 dx. Now let me note something, that by the time you begin to advance in calculus, you will notice that you will soon find out that there is a difference between this delta and dx and this d, these two notations. This one is used for partial differential and this one is used for complete derivative. This one means derivative and this is partial differential. Is that okay? Partial derivative. Does that make sense? But for now, let's just use it together. Is that okay? All right. Because when you begin to do order of differential equation and all of those things, you know that there is a difference. Okay? All right. So f of x f of x plus dx will be equal to x plus dx. We'll open this bracket. Okay, let's already open the bracket. Let's try to already open the bracket. This time this will become x cubed plus x times 2x dx. That will be 2x squared dx plus x times dx squared. That will be x dx squared plus this times this. This has multiplied everything here. So let this multiply everything here now. So this becomes x squared dx. Notice I did not say dx cubed. This x squared is not equal to this tiny change, very insignificant change in x. Okay, so it doesn't add up to say x squared times this is dx cubed. It's only dx times this that will give us something. Let's advance. We are going to see this. So this times this is this. Then this times this will be 2x dx squared plus 2x dx squared. Okay, plus dx cubed plus dx cubed, then plus all of this. Is that okay? If that be the case, then this our function becomes x cubed plus, is there any 2x squared, any x squared dx? Yes. This guy plus this guy will give us 3x squared dx. 3x squared dx, because they are like terms. This guy plus this guy will also give us 3x dx squared. 3x dx squared. Then plus dx cubed, then plus our 4x plus 4 dx. Okay. So remember that this is what we started with. Therefore, our f prime of x will now be equal to, recall that it is always f of x plus dx minus f of x all over dx which the limit of this as dx tends towards 0. This is always our f prime of x, okay? So what is f prime of x in this case? F prime of x will be equal to the limit as dx approaches 0 of f of x plus dx will be equal to what? This, all of this, which will be x cubed plus 3x squared dx plus 3 plus 3x dx squared plus dx cubed plus 4x plus 4 dx minus f of x. F of x is x cubed plus 4x. X cubed plus 4x minus all of this. Okay? So, all over everything over dx. Okay? If that be the case, then f prime of x will be equal to the limit of that as dx tends towards 0 of x cube. Okay, so you know that these two guys become negative, so this guy will take care of this guy, and 4x will become negative too, to take care of this guy. Okay, so let's already advance. This will become the limit of this 3x squared dx plus 3x dx squared plus dx cubed plus 4 dx all over dx. Okay, so the last stage now is going to be f prime of x is going to be the limit as dx approaches 0 of, now this guy, we're going to split this guy for all of the entities there. So that becomes 3x squared dx over dx plus 3x dx squared over dx plus dx cubed over dx plus 4 dx over dx. This takes care of this. This takes care of this. Okay? This takes care of 1. This takes care of 1, which remains 2. So f prime of x will be equal to the limit. Let's immediately take the limit as dx tends to 0. If we take the limit as dx tends to 0, f prime of x will therefore be equal to, this will be 0, this will be 0. Our answer will become 3x squared plus 4. Alright, so it is from this assumption that the general principle of differentiation was derived, since x squared eventually gave us the derivative of x squared eventually gave us 2x, and the derivative of x cubed plus 4x eventually gave us 3x squared plus 4. Then we can surmise that the derivative of any x raised to power a particular n exponent dx, it will be equal to n will come down, n times x raised to power that n exponent minus 1. And this is what we call the general principle. In the next video, we are going to be solving many more questions on the topic of differentiation or differential calculus. God bless you. Do well to subscribe to the channel and click the bell notification. And God bless you as you share with your friends.